we've lost some people. Oh, I guess they hadn't said they're going to record yet. Yeah. Okay. Well, we have been looking at regular singular points, and I thought a couple of things today. Somebody else wants in, that's good. Get us up to speed here. Just a second, I'll do something else while I'm waiting on people. So I'm waiting on somebody to get in here. By the way, there's certain things that we were warned are going to be shutting down around campus, and some computing services won't work and some emails won't work and stuff. Has anybody been affected by that yet? For example, I can't get Blackboard to come up at the moment. I don't know why that is. Try that again. Aha, there's a person waiting to get in. I'm waiting because there were 6 people sitting out there a little while ago, and now there's not. So I don't know where people went. Just one more moment. There's somebody coming back. Waiting room. Something's going on because of people in and out. So I may as well, while I'm waiting, do something here. Huh. There's definitely something going on. Are you guys still out there?
Yeah, I'm here still.
Some of you are.
Yeah.
Okay. Well, if I lose you, if we lose you, we'll just have to. I mean, I'll tell you to read the last section of the chapter, and then we'll be starting chapter 6. So this seems to. Okay, something's now working again. And okay, it's just amazing things are just not working. One more second, maybe I'll have what I want up here. Started working. Wow. No, I can't wait for that to work, so. Okay, so basically, I guess we go on here. For those of you who are watching the video here, we've had a pause is because university stuff is not working partly at the moment. Anyway, in chapter 5, what we've been talking about is regular singular points, and I'm going to put on the board some things about that. Now I have more people coming back. Maybe by the end of class, we'll have everybody in the class. If anybody knows the phone number to Murphy Owenby in our class, he's been trying to get into the room. Yeah, I'm sorry, you're right here. Yeah. I see this and it's not letting you in, right?
No, he's my roommate.
Oh, here it
It's
is.
your roommate trying to get in.
Yeah, yeah.
I remember.
So what do you want me to tell?
That's why I was confused by the name here too.
Oh,
He's in, he's in now. Okay. He's been trying to get in for 10 minutes.
Oh, gotcha.
Okay. That's what I was worried about. So the section 5.6 in the book, which is on page 224, is where the author does the stuff in general. And I can't sort of emphasize it enough in terms of how you set it up, because you've got to set the stuff up right, or the stuff that the book talks about, or the stuff that I talk about. And everybody knows all this stuff, I presume. But anyway, we define little p of x to be capital Q over capital P and so on, and little q be capital R over capital P. And those are the things we test to see whether or not they're analytic at whatever point it is that we're involved with. A lot of times the point will be 0. Sometimes the p of x will involve something besides 0, like 1 plus x or x squared minus 1 or something. Anyway, it's the p of x that is 0 that causes trouble, as you know. And also most of the problems that we do will be polynomials. And so ordinary points are just where the p is 0, and singular points are where the p is not 0. I'm sorry, I think I said that wrong. P of ordinary is where it's not 0, and when p of x is 0 for a given x, that's a singular point. Then we have to test it for regular, and regular singular points have to do with whether or not x p of x and x q of x are analytic. Again, if p and q are analytic, then it's an ordinary point.
Isn't it x squared q of x?
It is x squared, thank you. X squared q of x. Now, if we're doing this at some place else, like x naught, then you have to test x minus x naught p of x and x minus x naught squared q of x. Okay, and since most of our things are 0, you get used to doing that most of the time. Okay, now what comes out of the regular singular points, right away we have something called an indicial equation, and that is r times r minus 1 plus p sub 0 r plus q sub 0. Now what are they? Well, I may not have room to write them here, but if these things are analytic, these things, the p things and the q things, are power series. And so you'll have a q naught, you'll have a q1x, or x minus x naught in this case. You'll have power series. Over here, I'll have a power series. The constant term is p naught. The next term is p1 and so on. And so we're interested in what the q naught and the p naught are. And you can find those by taking the limit of either xp of x or x minus x naught p of x as you head toward x naught, and see what those are. And those you stick in here, and we solve this equation, and we get 2 roots. Okay, so that's a sort of a review. And by the way, what you'll find, if you haven't really studied it very much yet, on page 229, you have a theorem, 5.6.1. And that theorem spells out everything that theorem 5, the section 4 and 5 talk about. And so what I'm kind of doing right now, without saying so until this moment, is I'm kind of going through that theorem on page 229, because that's where the author summarizes everything into a series. Now, the only problem to me when I read that stuff is sometimes he refers to equations by numbers, like equation 26 or equation 22. And sometimes when I'm lazy, I don't want to go back and look and see what those are. I hope you guys aren't afflicted in the same way. But on this page, 229, he, let's see, refers to things, formula 21 and 22, that kind of stuff. And what I want to write down and find is the thing on page where is it? I want to do f of r plus n. Okay, it's on page 225. The other thing we need to remember for doing this stuff is the formula 8, which I don't like to use as number, but that's f of r plus n. And you know, I told you the other day I like sub k instead of sub n. But anyway, as far as what I'm writing on the board right now, he uses k for the subscript, and you have a sub k, and then you have r plus k. You'll have to get used to this symbolism plus q sub n minus k. And I'm going to talk a little bit more about that in a second. This is when n is greater than or equal to 1. So basically, the coefficients that we'll try to find that will tell us what the a sub n's are. Now, what in the world is that? Well, our solutions, we're going to have two solutions that we look at, and one of them is going to involve a sub somethings. And so generally, before we tailor it more carefully, we'll have x to the k or x minus x naught to the k, depending on whether the x naught is 0 or not. And then we will have a power series. And so if I write that a naught plus the sum from 1 to infinity, ak x or x minus x naught to k. Okay, this is what solutions look like, at least when we start. And then when the book and I deal with it, we start first with x positive, then we do x negative. In the end, you find out that what we need to do in general is stick absolute values around here. And this is a general look of y1. Y sub 2, the other one, depends on the nature of the roots of the initial equation. So the y2 might be something different. Generally, what it might mean is it might include y1 and it might include a logarithm. We'll talk more about that later. Anyway, these are the a's I'm referring to when you're trying to find these numbers. This thing I've circled is a recurrence relation, and let's talk a little bit more about that. Yes.
On your y1 of x, is that supposed to be x to the r1?
This should be actually r.
Okay.
Yeah. Thank you. Trying to do this too fast. So it should be r power. Sorry. Yeah. Anyway, and it will be, because the first one is going to be r1. Of the two roots, as we said already, I'm trying to cover too much in a short period here. We always pick the first root to be the biggest. And so that will be the biggest one. So it should be the power r1. Thank you. Okay, so that's the general idea. And so we need to find out what these are. Well, the a naught can always be taken to be 1, because in the equations, as you saw the other day, you have, when you stick the second derivative and the first derivative and the function things like this thing into the equation and simplify it, you will get an a naught f of r for a constant. And since f of r is 0, it doesn't matter what the a naught is. And so people always pick the a naught to be 1 here. And so on 229, that's what you should see in formula 21. So what I was trying to write up here, and I wrote it incorrectly, is formula 21 on page 229. Now, so that's going to be true no matter what the P, the Q, and the R are. These are the things you need to figure out. And so in a given problem, which is what we should be trying to explain by example, in a given example, we have to figure out the A's from what the P's and the Q's are. And the P's and the Q's are here. Now, I want to talk just a second about this sum from 0 to n minus 1 of this r plus k p sub n minus k plus q sub n minus k, that's a coefficient of a sub k. So if we write that out, and this is something you should do, and I'm missing a piece over here, but that's okay right now. I'm not trying to do the whole thing. This right here, if k is 0, we get r p sub n plus q sub n a sub n. And if k is 1, we get r plus 1 p sub n minus 1 plus q sub n minus 1 a sub n minus 1. Now, as I tried to say the other day, what we're doing is counting down instead of counting up. What you're used to seeing here is the K1 is x to the 1, and so you're used to seeing A1, then you're used to seeing A2, then you're used to seeing A3. Well, the way this is written is you're seeing them backwards, so to speak. In that, the very second to the last one would be when K equals n minus 2, and that would be R plus n minus 2, P sub n minus 2, which would be P2 plus Q2, and that would be the coefficient of A sub n minus 2, and then you would have an R plus n minus 1, P sub 1 plus Q sub 1, A sub n, well, the last one here, when I put in k equals n minus 1, I'll get n minus 1 here. Sorry, I've got something wrong here. I'm not, whatever I said it on the video is going to be wrong for a second here. Just a minute. Because I told you the other days you can get yourself confused here. This should be A sub 0. Oh, sorry, leave this alone. This should down here should be, when I let k be 0, this should be A sub 0. This should be A sub 1. And finally, this should be, when I put k equals n minus 2, this should be n minus 2. So the A's are going up, but the Q's and P's are going down. This is why I decided to write this down for you guys, and I just confused myself here. You have to be very careful about this stuff. But generally, for the problems that we have, we might only have a finite number of P's and Q's. Meaning, in a problem we did the other day, if you remember, P naught was 1 and P everything else was 0. Q naught was 1/2, Q1 was 1/2, and everything else was 0. So a lot of time when you're dealing with a problem, this is kind of a messy thing to look at, but if all the Q's above 2 are 0, then a lot of these don't exist. So if you had Q10 here, it would be 0, it would be gone. Q9 would be gone, and so forth. And so, although it looks like a beast, a lot of times when you have only a finite number of the P's and Q's, this actually comes out and collapses down to almost 1 or 2 terms. Okay? Now, but you need to do something that I didn't do a very good job of. You need to write it down correctly, because it's bad enough when you have it written down correctly to interpret it. Okay? Except, as I said, the good news is that a lot of times, a lot of these terms are gone. Now, when they're not gone, this is always going to be complicated. And what we're trying to do is we're trying to solve for A sub n. And so what you get is this sum here, and you get f of r plus n downstairs. Now, maybe, what do I mean by that? When we get this stuff, and we have 2 roots, one of the problems is when the difference of roots is an integer. When the difference of roots is an integer, then when I'm doing the smaller root, So I have R1 is bigger than R2. When I'm doing Y2 instead of Y1, that's the smaller root. So let's suppose that the smaller root is 1 and the bigger root is 5 for a second. When I'm doing this kind of stuff for the smaller root, what is R, if R is 1 and R1 is 1 and R2 is, I'm sorry, if R1 is 5 and R2 is 1, then when I have 1 here, I have 1 plus n. Well, when I get 1 plus 4, that's 5, and f of 5 is 0. And so the process, when the difference of these two things is an integer, you can't always divide by this thing out in front, because when you take the smaller one plus something and get the bigger one, f of that bigger number is what's 0. So you can't divide by it. That's why we have to separate. Earlier in this semester, we had a characteristic equation. We had 3 different kinds of things: real and different roots, real and equal roots, or complex roots. Now we have real and equal, real and not equal, and complex, but that real and not equal includes 2 separate cases. One where the difference of the 2 roots is not an integer, and one where it is. So you'll notice when it's not an integer, then no r plus n is an integer, and therefore you never have it. When you're dividing, you never have a 0 in the denominator. That means you can always do it. So the more complicated cases when you can't always do it. So I'm hoping that will kind of come through. Anyway, what I'm trying to get at here is we're trying to find an, and what is it in terms of? It's in terms of A0, A1, A2, A3, A4. In other words, if all these things are here, then the nth one may depend on all the rest of them before it. And what you hope is that a lot of these drop out, and so the nth one will only depend on maybe the n minus first one or the n minus second one or something like that. But different equations have different situations. So what does the author do? The author gives you a section 7 where he does 3 examples. And so that's what I want to talk about a little bit next. But before that, when I say next, I want to do something else first. I want to look at the other example that's in 5.6 and sort of talk about that. So I'm sorry about this. As I said, if you want to have some fun, you try to explain what I'm talking about to your sister or your brother or something. It's hard to talk about because there's so many little picky things you have to be careful about. And so I wish you had a better teacher, but you don't, and I'm sorry. But you don't have much to do without that. Some of you could have been smarter if you had not taken honors at all, then you would have missed all of this. Anyway, we have 3 plus x y prime. This is the example 1 minus xy. And so this is one example. Then the author provides 3 more called section 5.7. And what you guys ought to do is study all 4 of these as much as you can. He goes into a lot of explanation. There's no way I can talk about 5.7 in 50 minutes or even a couple of days. It's very complicated because it's intensive in terms of figuring this stuff out here that I'm trying to point out. So anyway, what we get, and some of this is easy. You know what P of X is easily. So we don't normally worry about that because what we do is we worry about Q of X over P of X. And so just in terms of my space here, this would be what I'm talking about. And R of X over P of X, that is going to be minus X over 2X times 1 plus X. And then you look and you hope that there's something you can cancel. In this particular case, I can cancel a X and so on. So you can always make those up. Now, what are the ordinary points of this equation and what are the singular points? Well, all you have to look at, since these 3 are polynomials, is where is this first thing 0 and where is it not 0? It's 0 at 0. So we have 0 and we have minus 1 are singular points. This is the kind of preliminary to solving the whole problem. So if I were asking you to do a power series about 2, so you do x minus 2 powers, you would just, this is 2 is an ordinary point, and you would just be doing these normal things that you did like in the first couple of sections. Okay, and you'd have an interval around 2, and notice what we'd have to avoid is things around -1 and things around 0, because those are the singular points. So you'd have an interval around 2, and you remember, you look at the distance to the places, and that's going to tell you the radius that you can do. And you would do an ordinary thing just like section 1 or 2 or whatever, I think section 2 and 3 in chapter 5. Okay, well, but where we are right now is we're doing these bad ones, these singular ones, because it's more complicated. So that's where this stuff we talked about here comes in. And what we need to look at 2 different things. And what the author does is he first looks at 0, and he says it's a regular singular point. He says that. Why is that true? Okay, well, what you want to do, this is little p of x, and this is little q of x over here. And so I want to multiply x times p of x when I'm doing this singular point 0. We'll have to do a different singular point, maybe on a different board in a little bit when we do -1. But xp of x, I look at that, xp of x is 3 plus x over 2 times 1 plus x. That around 0 is analytic. This denominator here actually, when you play with it, is the sum of a power series, of a geometric series. But in any event, when you just look at it, this is not 0 at around near 0, and it's a rational function, and we just say, hey, that's okay. This is analytic. The other one is when we multiply x squared times q of x, and if I do that, I get something else here. Hoping I haven't made any dumb mistakes. Once again, 1 plus x in the denominator doesn't cause any trouble for making power series. And so, and let's review that a second. If I have a r to the k minus 1 from k from 1 to infinity, this is a generic geometric series. If absolute r is less than 1, then this series converges, and it converges to a over 1 minus r. So why do I talk about this 1 plus x in denominator being geometric? Because if you think about this a little bit and just embroider on this just a little bit, 1 minus x is 1 plus x. So if I have 1 plus x in the denominator, it looks like 1 minus x. And so if I would take this as the a over 1 minus r and go backwards, the a is 1 and the r is minus x, I get minus x to the k minus 1, and I have a power series. I'm sorry, a geometric series. Okay? So when I see something like this in the denominator, now I've got a more complicated thing, but what's the more complicated thing? It's multiplying by minus x squared over 2. Well, multiplying by minus x squared over 2, just I can take the x squared in here, and I'll have k plus 1 instead of k minus 1. I can put the minus in here as one more minus 1, and I can play with the minuses, and I can put the half in. And so I can make this a nice power series by just realizing it was a geometric thing. And I get an analytic function here. Now, that's all just kind of extra stuff. If you need to find out what P0, P1, P2 are, which you probably do because they occur here, you might need to do what I just did. All right. But the second thing, to find the initial equation, to see what case we're in, we want to take the limit of xp of x as x goes to 0 and see what we get. In this particular case, we get 3 halves. We want to take the limit as x goes to 0 of x squared q of x and see what we get. In this case, we get 0. This means P naught is 3/2 and Q naught is 0. So what's the initial equation? F of R is R times R minus 1 plus 3/2 R, and that's set equal to 0. So you can factor R out of there. You have R minus 1 plus 1.5. So I'll have R plus 1/2. So the two roots of the initial equation are 0 and minus 1/2, if I didn't make any dumb mistakes. Now, so what's R1? R1 is 0 and R2 is minus 1/2. Do they differ by an integer? And his answer is no, they differ by a fraction. So we're in case 1A in the book. And that says that we have two solutions. One of them, I've run out of room as usual, but y1 is going to be absolute x to the 0 sum 1 to infinity. I'm sorry, I need a 1 plus this 1 to infinity a sub k, and we write a sub k 0 here because we want to distinguish between the coefficients for the first term and the second term. This would be what we have for the first one, and y2 in this case would be absolute x to the minus 1/2, and we'd have the second one. Well, we need to go back to 229 and see what the second one looks like, and the point is, when you do that, which you need to do, so I'm going to do that like I haven't done it before. Oh, that's number 22, and hey, that looks just like the first one. And so basically I copy the same stuff here. It's 1 plus the sum from 1 to infinity. Just don't have much room. Now it's ak of minus 1/2 x to the k, and I now have got the form of the answers. That doesn't mean I'm done. Now I need to create all this thing to tell me what all the A1, A2, A3, A4, and so forth on. Now, let me expand that just a little bit right here to show you that it's not terrible, because usually we don't ask you to find all the terms. Sometimes if they're easy, we find the general terms. Sometimes we just find the first 3 or 4 because it's too complicated. So if I want to find f of r plus 1, a sub 1, that's going to be the sum from 0 to 0, because if n is 1, that's 0. What is the sum from 0 to 0? That just means you stick, it's just one term. So this sum doesn't enter in really, it just becomes a sub 0. The r is, well, in general r. In this case, k is 0. So it's r, p sub n minus k. K is 0 and n is 1. That's p sub 1 plus q sub 1. Whatever the p subscript is always the same as the q subscript. So once you figure out what that one is, you know what this one is. And just a second, I need to be careful here. So that's equal to 0. So again, my problem is space here. And I'm erasing too much probably because we have to do the other root. But what I'm trying to say here is f of r plus 1, a sub 1, plus a sub 0, r p sub 1 plus q sub 1 equals 0. And so what's that going to tell us? That's going to tell us what a sub 1 is. Now, where are we? If r is 0, then we write a sub 1 of 0, and we have a sub 0 of 0, by the way, is always 1. And so what we would have here is f of 1, a sub 1, which we don't know, plus 1 times r is 0. So that's just 0 plus q1, whatever q1 is. And so that's 0. So in this case, depending on what happens here, we can find out what A1 is. I'm supposed to know what f of r is already. I stick F1 in here, and that tells me something about A1. Then I go back and I do the same thing with 2 and 3 and 4. And the point is you build up and you see how each term, each A sub K term depends on the previous ones. Now, the second half of this problem is to look at the second root, which was, I believe, -1/2. Okay, so now we're going to do the same stuff, except the R is going to be -1/2 and stuff. And according to this, it's the same thing. So we need to find these A sub K's, and you do the same thing in this particular case. And so if you look at the example on page 226 and 227, you will see that's exactly what he does, except, wait a minute. Now, okay, this was what I was led, I think, astray by my student who's here today. Okay, the second problem when we did this, I believe, was not -1/2. That's the second root of for the two things for the first case, 0. The second thing is -1/2 power. All right. The two singular points, I erased the equation. If you remember, the problem was 2x times 1 plus x y double.
Oh, yeah.
So, as I said, I was struggling. Remember, it was a +1 or -1. My student here, I only have one student here today, said, oh, it's -1/2 because that's this root here. This was the second answer to the root at 0. So, and so I bought into it for a few seconds and then went, oh, something wrong. The second one is -1. And so we need to go in and look at x plus 1 p of x and x plus 1 squared q of x and do the same stuff we did before, but with this new stuff, okay? And what about the power series? Are there going to be x here? And the answer is no, it's going to be x plus 1 here, okay? And so on. Now, what kind of a singular point is this one? Well, I'm going to have a new f of r because I'm going to have a new p naught and a new q naught. When I do this, this changes. And so I got a new solution. So in the second case, I don't know if I'm in 1a or 1b. Now in the book, it says when the point x minus 1 is a regular singular point and p naught is -1 this time and q naught is 0. So the roots of the initial equation are 2 and 0. So we're back in case 1 again. All right. So, but the roots this time are 2 and 0 instead of 0 and -1/2. So R1 this time, so what are our solutions going to look like around -1? They're going to look like x squared and x to 0, which is not going to be there. But there's still, 2 and 0, the difference is an integer. We're not in case 1a again. We're in that other case. The difference is 0. So that means the second one is no longer what the first one was. I got to look back in set theorem 5.6.1 to see the form of the second answer. And you're going to see that it involves a logarithm term. And so once you know that, then you go back and you start doing the same stuff here again. And everybody, I think, or at least most of us who are students of this, that when we're learning about this, we kind of need the book to be able to remember all this different stuff at once. Therefore, when we take a test in this, you'll be able to use these formulas from the book. Okay? I don't expect you guys to just learn all this stuff so you can just repeat it all. I hope you can, but I don't expect it. Now, okay, so let's go and look at section 7, which is like, oh, the new section. It's just the same stuff with new equations. 3 equations. They are all the same name, but they have different types for the same kind of equation. Now that's like the Legendre, if you remember. We had Hermite equations, and we had various equations. So what we have here, it's a famous equation. It comes in all kinds of places. We have x squared, we have xy, and over here we have x squared minus nu squared y equals 0. And this is called Bessel, B-E-S-S-E-L. This has the name Bessel, Bessel's equation. And the three examples come from letting the number nu, and Greek, basically this is just nu, okay? And it's like what a cow does, not what a cat does. It's not new, I mean, it's new, it's not new, okay? Like Buick is Bu. If you didn't say Buick, you'd say Buick for the car. Well, this is new. You probably know that. Okay, so what does he do? He says we're going to study nu equals 0, separately nu equals a half, and separately nu equals 1. So the three examples in section 5.7 are just like that example we just tried to do with his new equation, 3 different examples to see what you get. So what's the first example? He does the first example on page 231. He says Bessel's equations of order 0. So that means this is going to be called an order. Okay, so if the order is 0, the equation is x squared y double xy prime plus, if nu is 0, x squared y. This is the equation that we're going to study in the first section. And we've got 6 minutes to go here in the class. He writes all this out for you. Let's just talk about it a little bit. He says, as we have already noted, in other words, in a previous example, we had to figure out what are the singular points. And so Bessel's equation already came up in the previous section as an example. And so you see the x squared here, 0 is going to be a singular point. Okay. And what does that do to the initial equation and stuff? Well, we have to figure that out. But he said, we've already seen it. He said, we've seen that the initial equation has 2 roots, and the 2 roots are 0 and 0. That's pretty simple. So the R1 and R2 are both 0. So now we have equal roots. And the only good news is that they are both 0, which means that's going to simplify some of these complications here, because if the root 0 is going to wipe out some of the more complicated multiplications. And so you get right away a recurrence relation. In other words, you're able to quickly solve this problem here. And you get a recurrence relation, which is on page 231. And then he spends the rest of the page showing you what the coefficients are by solving that equation. And he gets, in this case, a general, and Bessel's equation has been studied very hard. And therefore, somebody figured out the general solution, what A sub k is in general. And that's what he's writing down here. He shows you the pattern at the bottom of page 231. So that's y1. That's pretty easy. You'll notice there is no x to the r out in front because r is 0. Okay? And then he shows you some pictures of, and the name of this first y1 is a Bessel function of the first kind of order 0. So remember, we find y1 and we find y2. When you find y1, it's going to be first kind. And the nu is going to tell us the order. So the first kind of order 0 means the biggest root. In this case, both roots are equal. Okay. And then this is going to be the second kind. So this is doing the same thing we did in the previous example. Okay. And you find the second kind. Now, what's the trouble with the second kind? Well, the second kind, he says we use equation 17 in section 5.6. I wish you wouldn't do that. I wish you'd write it out. Okay. And I'll let you read through that because we're down to 3 minutes left. I want to tell you what the other two are. Anyway, this second one is where it takes 2 pages to talk about. Okay. In other words, the second solution is more complicated. And if you look on page 233, the second one is this Wilder form, or number 13. And the other thing he throws in here, if we were just doing this ourselves, we would not have what comes out on page 233. He says, instead of Y2, see, we've been learning, we've been trying to find Y1 and Y2, and we've been sort of not doing much about Y2 so far. Well, when he finally does an example where he finds Y2, he says in the middle of page 233, instead of finding Y2, the second solution is usually taken to be a linear combination of the one we already did and the Y2 you find. So you find the Y2, but we don't call it Y2. We change it by taking a combination. What this is like is saying, I have one solution, e to the x, I have the other solution, e to the minus x, but I don't want to do that. I want to talk about hyperbolic cosine instead. In other words, if I take half of this and add half of this, I get this. And so he wants to talk about this one and this one instead of these two, he says, in this problem. This is not necessarily 100% the same, but the idea is he gets 2 answers, which you make combinations of. They say, I don't want to do that. I want one of the answers, but the other one, I want to switch around and do something else. And that's because in certain modeling, it turns out that we need to have the Y1 and Y2, the Y1's important, and that's called J sub 0 in this case. In other words, we rename it. In Bessel's equation, one solution is called J sub 0. Why is it called J sub 0? Because it's the 0 order and the root 0. And so it's called J sub 0. And then the second one, Y2, we combine with the J sub 0 to get what's called a second one. And that second one is called Y sub 0. And you can read that. And so we get 2 answers finally. And the second one involves a logarithm. Okay. And I'm beginning to run out of time. So the second example is to do the Bessel function of order 1/2. So first kind of order 1/2 and second kind of order 1/2. What does that mean now? That means the nu is a half, and we find the Y1 and the Y2. This one we call the first kind of order 1/2, the other one second kind. And then we do order 1. This is the third example. So please read the whole section. It's just 3 more examples of the kind of stuff we got to do if we're trying to understand what regular singular points are. Okay. Now, in the exercises, he gives you a couple more famous names, and they'll be little wrinkles off what we're doing here. But the whole game is to, I'm running out of time here, the whole game is to do this stuff about regular singular point, find the initial equation, get 2 roots. We have a way of finding all the coefficients once we do that. We have different, depending on what the roots are, we have 4 different cases. And if you kind of know that, you kind of know what we expect you to get out of this chapter. Monday, I'm going to start talking about chapter 6. I have already put in Blackboard notes on chapter 6. Okay, so when you get around to that, you can look. One of these days, we need to have an exam on the stuff we have just talked about, but I think it'll be a